Hello, everyone. Welcome to webinar number 3. Today we're talking about mechanics. So I've got 8 more problems for you. So hopefully we'll get through all of them. And let's get going. So some of the problems will be similar to the ones in the assignment. Some are not. Let's get uh, let's get going. Right, so mechanics part 2 and 17th of September. As usual, we have the Q&A open. If you want to find the Q&A, it's you need to press more and then Q&A, and you can ask a question. And either me or Konstantin, one of our tutors, will be able to answer that. Perfect. So problem 1, a point travels half the distance with velocity v0. Okay, so let's get to drawing. It's very important to draw a diagram. So half the distance with velocity v0. The remaining half of the distance is covered in 2 equal time intervals. So the first half of the remaining time, it moves with velocity v1 to some point, and then it travels with velocity v2 half the time. Find the mean velocity. Yes, find the mean velocity of the particle. Okay. So you've probably seen the question like you travel half the distance at speed 40 and second half at speed 60. Find the average speed. And the answer is not 50, right? Oh, what am I doing? Is it? Nope. Average speed is not 50. And that's not factorial, not 50. Right, so we know that the average speed is the total distance divided by total time. Okay, so let's say we have the total distance. Let it be 2s, and this is that means this distance is s, and then we have time t1, so s then time t1, and the distance is v1 t1, and this is v2 t2, right? So we can say the total distance is 2s divided by the total time, which is, let's say it's t0, and it's t0 plus t1 plus t2. Okay. Now, we know that v1 t1 plus v2 t2 must be s. So because this is half the distance s, and this is half the distance, another s. And let me just... Okay. We can start working with the time. v1t. Oh, sorry. We know that the time is the same. Sorry, I'm being silly. T1 is the same as T2, so it's T1. T1. V1 T1 plus V2 T2. Therefore, we can work out that T1, open bracket V1 plus V2, is equal to S, which and S is half the distance. Okay, then we have 2T1 in here. Okay. T1. T0, the time T0 is S divided by V0. And T1, okay, and from here T1 is S divided by V1 plus V2, as we can see. And therefore, we can substitute that into the average speed. So it's going to be 2S divided by T0, which is S divided by V0, plus 2T1, so 2 times S over V1 plus V2. And here, if we can divide by S, so we've got 2 divided by 1 over V0 plus 2 over V1 plus V2. And if we find the common denominator here, so it's 2 divided by V1 plus V2 plus 2V0 divided by V0, V1 plus V2. That's equal to 2V0, V1 plus V2 divided by V1 plus V2 plus 2V0. Brilliant. So that's the expression. That's the expression that for the average speed. We could have started with the simpler one, but I think it's given in the assignment, right? So imagine. Okay, I won't go there. Apologies. So we found the average speed, and that's the answer. Okay. Now, I really enjoyed this question. You have an equilateral triangle. And you have 3 particles. Let's call them A, B, and C. A has a velocity vector which is always pointing towards B. And it's moving with a velocity V. B has a velocity vector. So that's why it's called pursuit. A is pursuing B. B is pursuing C. And C has a velocity vector which is always pointing towards A. Okay. So what happens is A moves a tiny bit. So when A moves a tiny bit, let's say here, B moves and C moves. So now A is moving in this direction and C is moving in that direction. So they're moving in some sort of spiral, if you think about it. Let's say A has moved, so because it would be following like a spiral. B would be following a spiral, and C would be following like a spiral. So imagine some time later, this is the center of the 2 triangles. So A has moved into a new, A is here, B is here, and C is here. But A is still moving towards B is still moving towards C, and C is still moving towards A. So they're kind of converging onto one another. So you can see that if you have this, well, why are they spiraling? That's a good question. Because A moves towards B, and B moves towards C. So they do it at the same time. So, well, can we see triangles. Triangle pursuit. Pursuit. Yeah, you would get you would pursuit curves. So here's the triangle. You can see that this is what's going on. So the point A is always moving towards B, but B is moving towards C. So when the B has moved to this position, A is in this position, but you can see that the direction has changed. So the direction constantly changing. As A moves downwards, the direction will always change. So A is spiraling because B is moving, because B is moving along. And B is changing direction as well, because it's always pointing towards C. And C is changing direction. So it's moving towards A. So they're all spiraling. Think of this triangle. So think A has moved to this position. This is the new position of A. Now B has moved to this new position, and C has moved to this new position. So you can see that the triangle looks like this now. Now A moves a little bit further towards B. B moves a little bit further towards C, and C moves a little further towards A. You can see this pattern. And then you can see the new position of B, new position of C, and new position of A. A bit too much. This. And carry on. And you can, if you draw the line, B is spiraling. You can see this is the curve followed by B. This is the curve followed by A. And this is the curve followed by C. So they are sort of spiraling all the time. So the question is, how soon will they converge will they meet? They do meet at the center of the triangle, yes, and you can argue from the point of symmetry, right? Because they all move at the same time, they have to meet at the center. Okay. Now, whenever you're moving, like imagine at any position. So imagine O is the center of the triangle. O is the center, and you're at a random point A. And let's say you're at a random, you're at point A. Your velocity, imagine you have a velocity like this. It has two components. You have the radial component of velocity, this component, and you have the perpendicular component of velocity. The perpendicular component is the one that causes you to move in a circle. So if you have only only perpendicular component, then you would just move in a circle like a planet around the sun. But here you have velocity towards the center and perpendicular to the radial direction. So this is the radial component. And because point A will always be at the vertex of a triangle, or just of a new triangle, and the velocity is the same, v, v, and v, you can see that the velocity vector will always make the same angle towards the center. It's a 30-degree angle. and here it's a 30-degree angle. So this angle is constant and it's 30 degrees. So velocity vector, t vector of point A will always make a 30-degree angle with the line OA, AO, it doesn't really matter, with, let's say, vector AO, vector AO. All right, let's confirm that. Well, you have A, B, and C, and this is O. So this is vector AO, and this is the velocity vector. And because it's a it's a regular, sorry, it's an equilateral triangle, this is a 30-degree angle. Now imagine point A has moved, and now the new position of A is here. The new position of B is here. The new position of C is here. So this is A, this is B, this is C. Now this is vector AO, and this is the velocity vector, V. And it's because it's still an equilateral triangle, it's still 30 degrees. Okay. That means that the radial component of velocity is always, the radial component of velocity is always is always the same. So the radial component of velocity, which is this one, and it is v cos 30, is always v cos 30 degrees, or v square root of 3 over 2. V is constant. V is a constant speed. Yes, it is not decelerating. It's moving at a constant speed. And if the speed is constant, then to find the time, you only need to find the distance traveled. And the distance from A to O, the total distance traveled and in the radial direction is the length of AO, which is well, it's AO original. Let's say it's R0, 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 and R0 is, well, it's two-thirds of AH, and AH is the height of an equilateral triangle. AC, that's A squared minus, and this is A over 2, A squared over 2, using Pythagoras theorem to find the height is, so it's 3 quarters A squared, or square root of 3 over 2A, and multiply this, so that's equals 2/3 multiplied by square root of 3 over 2A. 2 cancel, so that's square root of 3 over 3A. Yes, and then we just need to find the time. Is R0, which is square root of 3 over 3A. The time to converge. Time to converge is how long it will take point A to reach the center. 2/3, because we know that the center of the triangle is 2/3 along the median line. So if you take the median line of a triangle, median then this distance is 2/3 of the median. The center of the triangle is the center of a triangle splits the median in proportion 2 to 1. So it's 2/3. Time to converge, t, is r0 divided by the radial component, v radial. So it's r0 divided by v cos 30. So it's square root of 3 over 3a divided by v multiplied by square root of 3 over 2. Square root of 3 cancels, and we get 2a divided by 3b. And that's the time. This is the answer. Okay. This question was provided, well, these questions were provided by Konstantin, and thank you very much for this lovely question. I really enjoyed it. Two bodies were thrown simultaneously from the same point, one straight up and the other at an angle 60 degrees to the horizontal. The initial speed of each body is 25 meters a second. Neglect air drag. Find the distance between the bodies at time 1.7 seconds. Okay, so that's a single point. And you know what? Why not do the experiment? Bet projectile. Motion. Okay, so one is straight up at 25 and shoot. Oh, so the particle goes up and then falls to the ground. And then the second one is 60 degrees. Right, 1.7 seconds. 1.6, 1.7 seconds. And then the, yeah, 1.6. 1.7. So now we know what we're looking for. So if they, after 1.7 seconds, one particle is going to be here, and one particle is going to be here. And we need to find that distance. Or we can kind of calculate it from here. But I'm going to do it in a slightly more formal way. I'm going to write down the equation of motion for the two particles. Equation of motion of a particle, because this is constant acceleration. So, equation of motion. The equation of motion, you know this as the Suvat equation. S is ut plus 1/2 at squared. Remember, S is a vector, and U is a vector, and A is a vector. And S is actually the change in position. This is a change in position. So it's, S is the final position minus initial position. So R0 is the initial position. And R is the final or current position. So I'm going to write this as R minus R0 equals UT plus 1/2 AT squared. And then I'm just going to write R is equal to R0 plus UT plus 1/2 AT squared. And that's the equation of motion of a particle moving with constant acceleration. And then for particle A, the particle A goes vertically up. One straight up, let's call it A, and the other at an angle B. So RA is equal to the initial position. So we can assume the initial position is 0, 0. Plus the initial velocity. The initial velocity is 0.25 because it's moving straight up. Times time. And plus the acceleration. So it's 1/2. I'm going to take 10 for simplicity. So 0 minus 10 is the acceleration because it's a vector, and multiplied by t squared. Okay, so that's the equation of motion of A. Of course, I can simplify that, but that's not important right now. RB is the initial position, so 0, 0, plus the initial velocity. So it is shot at 60 degrees to the horizontal. So it's going to be 25 cos 60 and 25 sine 60. That's the horizontal and vertical velocity times time plus 1/2. 0 minus 10, the acceleration is the same, multiplied by t squared. And the distance is actually the difference. Distance between is RB minus RA. Is the difference between the two vectors. Well, it's the modulus of that. Right. And we can find RB minus RA. So it's 25 cos 60 minus 0. Well, 25 cos 60. 25 sine 60 minus 25 times t. Oh, and this cancels out. Oh, that's super easy because we can see that these indeed cancel out when you subtract, and all you need is to substitute time. We know t is 1.7, so when t is 1.7 seconds, that is 25 cos 60 times 1.7, which is 21.25, and 25 open bracket sine 60 minus 1 times 1.7 minus 5.69 meters. What does that mean? Well, that means that horizontally, the distance is 25.25 meters, and we can see that. This is 0, and this is 25.25. So that's the horizontal distance. And the vertical distance, vertical displacement from A to B is minus 5.69. And you can see it here. It's 28 and 23, or 22. So it matches. And now the distance between is just the modulus of RB minus RA is the square root of 21.25 squared plus 5.69 minus 5.86 squared. And that is root of answer squared plus 21.25 squared 22 meters, 22.0 meters. So that's the distance. So, and well, it is does look very reasonable, right? You can use Pythagoras here. You can use Pythagoras. So this is about 20. This is 21.25 meters, and the vertical is 5.69 meters. So yes. So 1.7 seconds. It's not a 1.75. It's 1.7 s. Apologies for my penmanship. Okay, moving on. You have an inclined plane and you go up the plane and then go down. Does it take more time to go up, or does it take more time to go down? Or is it the same? What do you think? Well, it does say in the question, so but try to imagine it. Of course, there's no friction, then the time is exactly the same. But if there is friction, time is different. So you got an angle alpha, which is 15 degrees. And an object is launched up. It's probably not a ball, but like round objects. So it's shot at a velocity. Well, we don't know the velocity. Let's call it u. And there's a friction coefficient. It's found at the time of ascend. So it goes up a distance. Let's call it s. So assume initial velocity. Velocity is u, and distance is s. We do not know them. They remain unknown. Our answer cannot be in terms of u and s. Basically, our answer can only be based on the angle, and we will see that these two values will not play a role. So the answer is independent on the distance, and the answer is independent on the initial speed. Okay. So what's going on? So when it's going up, so we're probably interested in the acceleration going up. So we look at the forces acting on the mass, and we have the gravitational force, mg. We have the friction force this way, force of friction. We have the normal force, and that's it. So those are the three forces. And we're gonna split the forces into vertical and horizontal components, but not vertical and horizontal, but along the slope and perpendicular to the slope. So this is perpendicular to the slope, this is along the slope, x and y. X is along slope. And now we need Newton's second law. Newton's second law. We're going to split the mg into two components, like this and like this. This is mg cos theta, and this is mg sine theta. And the acceleration obviously is to the left. Acceleration is backwards. Newton's second law. So in the vertical, in the y direction, in the y direction, the particle is not accelerating. So it's not going up along the y-axis and it's not going down along the y-axis. So along the y-axis, the normal reaction force minus mg cos theta must equal to 0 because it's not accelerating. And along the x-axis, mass times acceleration. So acceleration is to the left. So mass times acceleration is equal to mg sine theta plus force of friction. But we know that the friction force is mu n. So we can write ma equals mg sine theta plus mu n. And from here, we can see that n is mg cos theta. So ma equals mg sine theta plus mu mg cos theta. And mass cancels. Acceleration is g open bracket sine theta plus mu cos theta. Well, it's obviously negative. Acceleration is negative, so decelerating. That's a deceleration. Okay, now going down. Can I make it slightly smaller? Okay, going down. Going down. You have the same slope. This is the x-axis. This is the y-axis. You have mg. You have friction force, mu n, and the normal force is n. And you're accelerating downwards. You have to accelerate downwards because if you're not accelerating, you would just go to the top and stop. All right. So now you split mg into two components. Because this angle is alpha. Oh, it's not theta, it's alpha. Apologies. So that's alpha. 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 So here you have acceleration is downwards. So that's mg cos alpha, and this is mg sine alpha. So mg sine alpha is, so who's doing the acceleration? Who's accelerating the body? Well, it's mg sine alpha minus mu n. So in the y direction, it's the same as normal force minus mg cos alpha is 0. So n is mg cos alpha. In the x direction, you have mass times acceleration is equal to mg sine alpha minus mu n. So ma is equal to mg sine alpha minus mu mg cos alpha. M cancels, and you have A equals G open bracket sine alpha minus mu mu cos alpha. Okay. So you can see that going down, the acceleration is smaller, and that does mean that it will take you more time. It will take you more time. All right, so now you can do Suvat because going up, Suvat. Displacement is s, initial velocity is u, final velocity is 0. Acceleration is minus g sine alpha plus mu cos alpha. And t is, well, t is t. Let's call it tau. And going down, s is s, u is 0, final velocity is, well, we don't know. Acceleration is g sine alpha, uh, g sine alpha minus mu cos alpha, and t is 2 tau. Okay, so choosing a suitable equation, I'm guessing we well, I'm guessing we need the equation without it doesn't really matter which equation we use. Let's say we find tau from here. We have final velocity equals u plus at. So the final velocity is 0 equals u minus g sine alpha plus mu cos alpha times tau. So tau is u. Oh no, just say u is equal to this thing, g sine alpha plus mu cos alpha times tau. And when do we use that for we need to find mu? No, I don't think we can use. I don't think we should use that equation. No, that's a bit useless. Sorry. Let's use the equation without u, without the initial velocity. Can we do that? Well, there is an equation like this, and it's looks like this: S is equal to VT minus 1/2 AT squared. So S is equal to minus 1/2, so plus 1/2 G sine alpha plus mu. Should acceleration going down also be negative? Well, no, we choose different, going up, the direction. We're choosing the different direction for each time. Going up, up is positive. Up is positive. Going down, down is positive. You know, I'm a bit, it's weird, but it works. Okay. So sine 1/2 sine alpha plus mu cos alpha times tau squared. Okay, and then okay. This is the distance. Then we have S is equal to, using ut plus 1/2 a t squared. Ah, yes, S is u, so 0. plus 1/2 multiplied by g sine alpha minus mu cos alpha multiplied by t squared, and t is 4 tau squared because it's double the time, 4t squared. Now we can equate them, of course, because s is equal to s. So s up is equal to s down, and that is 1/2 g sine alpha plus mu cos alpha tau squared has to equal to 1/2 g sine alpha minus mu cos alpha, 4 tau squared. Tau cancels, half g cancels, and we have sine alpha plus mu cos alpha equals 4 sine alpha minus 4 mu cos alpha. And here we have 5 mu cos alpha equals 3 sine alpha. Mu is equal to 3/5 sine alpha over cos alpha, which is 3/5 tan alpha. And now we can finally calculate the value. 3/5 tan 15. I won't try to calculate that without a calculator. It is possible, just not 0.161. 61. Right. Oh, that's a very nice question. The beautiful thing is that the initial speed and the final and the distance are not involved in the answer at all. You just find the answer in terms of alpha. Problem 5. Okay, a massless rigid rod. So we have a rigid rod, and the length of 3L is suspended horizontally by 2 vertical strings attached at each end. Okay. So there are 2 strings holding the rod, and 2 small masses are fixed to the rod, a mass m. So here, a mass m at a distance L, and a mass 2m, distance 2L, so 2/3 of the way. So that's L, L, and L. Gravity acts downwards with acceleration g. Right. Find the tension in TL and TR of the left and right fibers. Okay, so there's a tension in this rod, and there's a tension, so in this string, TL and TR. And of course, there's a gravitational force here. The mass of the rod is, oh, it's massless. Okay, there's no mass. Apologies. Okay, right, so we have, if we draw the rod, I always advise to draw the rod separately and show the forces acting. So there's a tension TL, there's a tension TR, there's a downwards force here, which is mg, and there's a downwards force here, which is 2mg. Of course, because it's in equilibrium, you can say that TL plus TR is equal to 3mg. That's the first equation, but that doesn't allow you to find TL or TR. Okay, so now we take the moments about point A. Moments about point A. And you can see that this force produces a moment clockwise. This force produces a clockwise moment, and this force produces an anti-clockwise moment. So you have moments about point A. You have mg multiplied by L. That's the moment of mg, because that's L, plus 2mg times 2L. So that's the moment of this force. Remember, moment is force times distance to the pivot, minus, because it's the opposite way, TR times 3L, and that's equals to 0. And therefore, I can say that TR is equal to MGL plus formula, so 5 MGL divided by 3L. So L cancels, so 5/3 mg. And TL, of course, 5/3, so it's 3 mg minus TR, which is 3 mg minus 5/3 mg, which is 9/4, 4/3 mg. Perfect. Now the right rope is cut. So we cut this with scissors, and then it hangs from just the left rope. So B after right rope is cut. Well, it will hang okay. So you have the whole rod hanging from a single rope, and that's a much easier question. So there's a tension, and obviously there are two masses here, mg and 2 mg, and TL is equal to 3 mg. That's an easy one, TL dash. And then TL after minus TL before is equal to TL after minus TL before is equal to 3 mg minus 4/3 mg, which is in fact 5/3 mg. So that's the change in tension on the rope. After it's, of course, initially it doesn't change. So if you cut the rope at R, I would imagine that there's no change in tension at L at instant. So it takes some time to settle down. Okay, problem 6. A box of mass M1 sits on a frictionless incline, which makes an angle alpha. So angle alpha, a box of mass M1. The box is connected by a massless rope to an ideal frictionless pulley to a hanging bucket of mass M2. So you have a pulley and you have a bucket of mass M2. Okay. Then the ratio of M1 to M2 is such that the box moves down the incline. So the box accelerates down the incline. So the bucket must move up the incline. Neglect friction and the mass and the moment of inertia of the pulley and rope. Okay, find the time it takes the box to travel a distance S along the incline. So distance S, so the box is traveling this distance. So we just need to find the acceleration, of course. All right, this is quite a straightforward problem. So as in any problem with several masses, we look at each mass separately. So looking at the mass M1. So it has a downwards force, which is mg. It has a normal force, normal reaction force, and it has a tension force, tension in the rope. So to draw the forces, you need to imagine. You need to imagine that you are the box, right? You are the box. Who's pulling you? Well, gravity is pulling you. The rope is pulling you, and the table, the incline is pushing you. So these are the three forces that you experience. Okay, and now we know that you're accelerating in that direction. Acceleration A. And therefore, you can write down Newton's second law. So you have this direction, and you have this direction, X and Y. So in the X direction, mg splits into components. So this is alpha. So this is mg cos alpha. This is mg sine alpha. In the x direction, so mass times acceleration is equal to the sum of forces. So mass times acceleration is mg sine alpha minus tension minus t. So who's pulling you forwards minus who's pulling you backwards. That's it. So for the y direction, the acceleration is 0. So 0 is equal to the sum of forces. And then you have 0 equals normal reaction minus mg cos alpha. And from here, you get that n is mg cos alpha. I've got a feeling that we won't need that, but nevertheless. Okay, so we've got two equations, this and this. Now for the bucket. So the box. Now the bucket. The bucket is much, much simpler. You have gravity pulling you down. Oh, M1A, M1. It's the M1, M1 and M1. Yes. M2G, and there's the tension in the rope. And the bucket is moving up acceleration. So mass acceleration of the bucket is the sum of forces. Mass acceleration, M2A, is T minus M2G. Inextensible means that both ends of the rope necessarily move with the same speed. If the rope is not allowed to extend, if one end moves at speed 3 meters a second, then the other end moves with 3 meters a second, right? So they always move together. If it's an extensible string, then one end can move and the other one could stay still. And that's your second equation. So that's equation number 1. That's equation number 2. And you can solve them simultaneously. You can add them, as a matter of fact. 1 plus 2. First equation plus second. So M1A plus M2A equals M1G sine alpha minus M2G. And that means that the M1 plus M2A equals mg sine alpha minus m2g. So the acceleration is g open bracket g times m1 sine alpha minus m2 divided by m1 plus m2. So we've got acceleration. And now we need the time it takes to travel a distance s. Well, that's an easy one. So it's a suvat. Suvat. Initial speed is 0. Final velocity is unknown. Acceleration is this thing. Is known. I don't want to. Okay. Is this. And T is question mark. T is question mark. So V is we don't know. S is S. So of course we use S equals UT plus 1/2 AT squared. So this is 0. T is equal to 2s divided by a, which square root of 2s divided by a, and that is 2g, oh no, so 2s divided by g m1 sine alpha minus m2 m1 plus m2. Okay. It is important that the string and pulleys are massless. That means that the tension at if the rope is massless, that means the tension at any point in the string is the same. So, no, if the string is massless, that means that on either side of the pulley, the tensions are no, sorry, at both ends of the rope, the tensions are the same. Pulley is massless and this frictionless means that there's the tension on either side of the pulley is the same. So basically, if the rope is not massless, then we couldn't say that this T is the same as this T. They would be different because if the rope is heavy, like imagine you have a heavy rope, you have more tension at the top and less tension at the bottom, like a slinky, long slinky. Images. Um, hanging. Hanging. Yes, you can see that at the top, so this is a heavy rope effectively. At the top is more stretched out than at the bottom. And that tells you that the tension at the top is different from the tension at the bottom. Okay. So T, let's call T1 and T2. T2 is greater than T1. So rope is not massless. All right. Cool. We got two more, and I think we might just might do it. Okay. So you have a metal seat of mass 32 kilograms. So you've got a seat of mass M2 is 32 kilograms. Massless rope, one end of a massless rope. So it has a rope passing over a pulley attached to the ceiling. So there's a ceiling. Okay. A spring scale hangs from the other end of the rope. Spring scale. So I'm assuming this spring scale is attached to the floor. I would be surprised if it isn't. Right. So basically you have a Newton meter. You have a spring here. It's a Newton meter. A boy of mass. So there's a boy of mass M1 is 64 kilograms. Sits on the seat and pulls down on the spring scale. Okay. The scale shows 600 newtons. What? Sorry. If it's okay, anyways, what that means, that's simply, so the reading on the Newton meter is 600 newtons. So the reading on the Newton meter is 600 newtons. And what we have, and that is the tension in the rope. That is the tension in the rope. Okay. Yes, but this is a dynamic system, so it's not in the system is not in equilibrium. Not in equilibrium. So we want to know what happens to the boy at the moment where the Newton meter shows 600, if that makes sense. Because uh, if you have a bathroom scale at home, not the fancy digital one, but just the normal one where you have a springy one, I'm sure one day you decided to jump on it. Right? You go ding, 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 and you could see how the arrow goes all the way, so you can make yourself really heavy or really light. If you jump on the scales, you go light. When you press on them, you get heavier. So basically, the boy sits on it, it starts bouncing up and down because there's a Newton meter. So the question is, at the moment when it's 600 newtons, what's happening to the boy? Okay, so if this is 600 newtons, that means that the tension in the string is also 600 newtons, and we're going to use that. So we have the boy and the chair. So that's a total mass of 96 kilograms. And there's a rope, there's a tension here, and there's the mg. mg. And we don't know which way acceleration is, but we know that tension is 600 newtons. But we know that mg is, well, 960 newtons because it's 96 kilograms. So the boy must be accelerating downwards. And so mass times acceleration is downwards force. Well, this is the sum of forces. So mass acceleration is mg minus tension, and acceleration is g minus t over m. G is 10 minus t, which is 600 divided by 96. 600 divided by 96. 6.25, 10 minus that is 3.75. So 3.75 meters per second squared. So boy is accelerating, rating down at 3.75 meters per second squared. I'm looking at the answer. I think it's a different answer, and maybe I didn't understand the question correctly, but all right. Final question 8. A triangular wedge is fixed to the horizontal surface. The base angles of the wedge are alpha and pi over 2 minus alpha, so that's 90 minus alpha. Particles of masses m and m lie in different faces of the wedge are connected by a light inaccessible string which passes over a smooth pulley at the apex of the wedge, as shown in the diagram. Okay, the contacts between the particles in the wedge are smooth. Okay, show that if tan particle m will slide down the face of the wedge. So we start with particle m. So we have a tension force T. We have the gravitational force mg. And we have the angle, which is alpha. And we have the normal reaction force. Let's call it N1. And we can see that this angle is alpha. So N1, so the vertical in this direction, resolving the forces in this direction, N1 must equal to mg cos alpha. And horizontally, that direction, well, we'll slide down. Okay, so let's say it's for slide down, acceleration down in this direction. So mass times acceleration is the sum of forces. So mass times acceleration is mg sine alpha. So that's the component down the slope. So that's mg cos alpha, mg sine alpha. Ma is mg sine alpha minus t, minus tension. So that's the first equation. Now for the second one, for the second mass, m, we have the tension force going up. We have the mg force going down. We have the normal reaction N2. And because it's going up the slope, accelerating up the slope, and this is mg sine pi over 2 minus alpha, and this is mg cos pi over 2 minus alpha. You can write that in this direction, so perpendicular to the slope, is N2 equals to mg cos pi over 2 minus alpha. But cos pi over 2 minus alpha is actually equal to sine alpha. You can check that. So, and sine pi over 2 minus alpha is cos alpha. These are important relations which you kind of need to know, or at least be aware of. And so that is equal to mg sine alpha. And now resolving the forces in this direction along the slope, you have mass times acceleration is equal to tension minus mg cos pi over 2 minus alpha, which is t minus mg. That doesn't make any sense. Sine mg cos alpha. Yeah, mg cos alpha. Okay, so you've got two equations, 1 and 2, and well, we can add them. Let's do 1 plus 2, and we have ma plus ma equals mg sine alpha minus mg cos alpha, and then acceleration is mg sine alpha minus mg cos alpha divided by m plus m. And m is going down if acceleration is greater or equal to 0. And if acceleration is greater or equal to 0, that means mg sine alpha minus mg cos alpha must be greater or equal to 0. So mg sine alpha greater or equal mg cos alpha. G cancels. So sine alpha divided by cos alpha is greater or equal than m over m. So tan alpha must be greater or equal than m over m. And that's the condition for positive acceleration, which we know. The particle will slide down the face of the wedge. Well, yeah, it's greater or equal or greater. Well, if it's equal, they will be stationary. If tan alpha equal m over m, then you have stationary. So yes, tan alpha has to be greater than m over m, although that's not that significant. The difference is not very significant. Given that tan is 2m over m, show that the magnitude of the acceleration of the particle, and it is maximized when this. All right. Okay. Well, we know that the acceleration is, we already know that the acceleration is mg sine alpha minus mg cos alpha divided by m plus m. And if we know that tan alpha is 2m over m, well, what can we do? Well, we can say that um, well, I'm guessing you have to work out the you have to work out the sign because G, sorry. Yes, there's a sine alpha here. Okay. Okay, the acceleration of the particle is this. Okay, so tan alpha is this. That means that small m can be written as m tan alpha divided by 2. So acceleration is mg sine alpha minus small m, so m tan alpha over 2 g cos alpha divided by small m plus, oh sorry, m plus m tan alpha over 2. And you can see that m cancels, as it should. And it's tan alpha times cos alpha. So it's g sine alpha minus tan alpha. Tan is sine alpha over cos alpha times cos alpha. So cos alpha cancels, divided by 1 plus tan alpha over 2. So multiply both sides by 2. So that's going to be g2 sine alpha minus sine alpha divided by 2 plus tan alpha equals g sine alpha divided by 2 plus tan alpha. Now, it is maximized. Well, let's find acceleration in terms of m. Acceleration is g, which is, so g multiplied by sine alpha. Oh, actually, why not? The acceleration is maximized when okay, for a certain value. Okay, so we can find the angle at which that value is maximum, but that's obviously 0. Sorry, obviously 90 degrees. Yes. So is there a limit? Is there a limitation? Well, I mean, it's quite a silly question, honestly, because if you put the wedge like this, that's when you have maximum acceleration, right? So if you have m big, m small, so alpha must be 90 degrees. Alpha must be 90 degrees. So if alpha is 90 degrees, so a is max, acceleration is max when alpha is 90 degrees. So you would have a is g multiplied by 1 divided by 2, 2 plus tan alpha. Does that make any sense? Well, 90 degrees, tan 90 doesn't exist. Wait, tan 90 doesn't exist, exactly. If you don't understand the question, which question are you referring to? Uh, right. Okay, so let's do some differentiation here. Okay. Maximum value. A is maximized. A is maximized if the derivative with respect to alpha is 0. That's how optimization works. When you differentiate with respect to alpha, and that's equal to 0, so we need to differentiate that. It's a little bit beyond the scope because we haven't done trig functions yet. So I'm just going to differentiate that. G sine alpha divided by 2 plus tan alpha. We're prime, so we are differentiating that. So we're using the quotient rule for differentiating. So this is harder than in your assignment, so don't worry about it. G sine alpha multiplied by 2 plus tan alpha minus G sine alpha multiplied by 2 plus tan alpha dash divided by 2 plus tan alpha squared. And that must equal to 0. And that means G cos alpha, because the derivative of sine is cos, multiplied by 2 plus tan alpha minus G sine alpha. And then differentiate that is going to be 1 over cos alpha, cos squared alpha. The derivative of tan is 1 over cos squared alpha, because sine cos alpha, cos squared alpha plus, yes, squared alpha plus sine squared alpha. And that's must equal to 0. And that means that cos alpha to, should we open the brackets? Yes, I think we should open the brackets. G obviously cancels. So we have 2 cos alpha plus sine alpha minus 1 over cos alpha. Oh no. Minus sine alpha divided by cos squared alpha equals 0. And then what can we do here? Multiply everything by cos squared alpha. Okay, 2 cos cubed alpha plus cos squared alpha sine alpha minus sine alpha equals 0. Well, that's equal to 0. And then we can do 2 cos alpha just a second. Oh, I don't have the yeah, I don't have this question. This is honestly a weird question. Okay, let's see if we can 2 cos squared alpha. Let's write down a function. So 2 cos cubed alpha. So where is my Desmos? 2 cos cubed x y equals 2 cos x cubed and 2 cos plus cos squared plus cos squared x sine alpha multiplied by sine x sine x minus sine x. And you can see that it's maximized at when alpha is this value, 0.89991. What's the significance of that? That is alpha is 0.89991, 0.89991, and that means that tan alpha is gradient tan 0.89991, 1.2599. And then we know that tangent alpha is 2m over m. So 2m over m is equal to 1.2599 and or m cubed. If you cube that, okay. So if you cube that, you get 8m cubed over m cubed. And cubed. Oh, that is 2. Nice. And that means that you divide by 2, so m cubed equals 4m cubed equals m cubed. Wow. Okay. With the slight cheat from Desmos, we got there, but hopefully you saw how I would use different tools to try to figure out what's going on. So let me just walk you through the last bit here. What I did. So when you do an optimization problem, you have to differentiate, and it is maximum or minimum when the derivative is 0. So what I did, I took the expression for the acceleration. I have the acceleration is g sine alpha divided by 2 plus tan alpha. Okay. Now at some value of alpha, this acceleration is going to be max. A is max for some value of alpha. Okay. And to find that value, we need to find the derivative. So we differentiate dA by d alpha, and it is equal to 0. So what I've done, I differentiated A. We differentiated A, so dA d alpha is that, and I made it equal to 0. Then I've got an equation which I couldn't solve straight away, so I put it into Desmos, and I saw that it crosses the x-axis at point 0.899901, and I substituted that in. Right, so this is because this is alpha, and the vertical axis is, well, with nothing. We don't know what it is. Oh, well, it's the derivative. It's the dA d alpha. dA d alpha. So the derivative is 0 at maximum. So at maximum. When A is maximum, dA d alpha is 0. And that's what I did. I found that point. I found the alpha. I found the tan. And I substituted the tan into my original expression, well, for tan. And then I found this relationship, which is a purely mathematical relationship, but we got there eventually. That's a good question. In this case, I don't, because all other values are just outside the range. Because you can see that 4 is alpha cannot be 4, because 4 is, you cannot have an angle of 4 radians. It's just too big. Now, and there are no other possibilities there. So generally speaking, when you do an optimization problem, you would always have just one possible point, and that won't be the answer. So yes, you are right. Strictly speaking, you have to, but it's not necessary. All right. Okay, I hope that was useful, and I hope you got something out of it today, and I'll see you all in 2 weeks' time. Enjoy.